There's a building material that gets stronger with age, repairs its own cracks, and lasts 10 times longer than concrete. Modern engineers won't touch it because it breaks every rule they were taught. Walk into a 13th century Gothic cathedral anywhere in Europe. Run your hand along the stone walls, the vaulted ceilings, the flying buttresses. The lime mortar holding those thousands of stones together is still strong, still flexible, still bonding after 800 years. Now drive past a highway overpass built in the 1960s or 70s. Notice the concrete spalling, the exposed rebar rusting and expanding, the structural cracks being patched with epoxy. That bridge has maybe 20 or 30 years left before it needs replacement, if it hasn't been condemned already. The paradox is brutal. Ancient and medieval building materials routinely outlast modern ones by factors of 5, 10, even 20. And modern structural engineers know it, but they're terrified to go back. In this video, you'll discover exactly what that forgotten material is, why it outperforms modern concrete and mortar by every long-term metric, why the construction industry abandoned it, and why engineers today are genuinely afraid to revive it, even though they know it works better. Section 1. The material: lime mortar and lime concrete. The forgotten material that modern engineers fear isn't exotic. It's lime mortar and lime-based concrete, the binding agent that held together nearly every significant structure built before the mid-20th century. What is lime mortar? Lime mortar is made by mixing slaked lime, calcium hydroxide, with sand and water. When exposed to air, it undergoes a chemical process called carbonation. It absorbs carbon dioxide and slowly converts back into calcium carbonate, essentially limestone, over months and years. This is fundamentally different from modern Portland cement mortar, which hardens through a hydration reaction in hours or days and never significantly changes afterward. Historical pedigree: lime has been used in construction for at least 4,000 years. The Egyptians used gypsum and lime plasters. The Greeks built with lime mortars. The Romans perfected hydraulic lime concrete by adding volcanic ash, pozzolana, creating structures like the Pantheon, aqueducts, and the Colosseum, all still standing. Medieval builders inherited and refined these techniques. The great cathedrals, castles, bridges, and civic buildings of the Middle Ages were almost universally built with lime mortar binding stone or brick. By the time of the Renaissance and into the 19th century, lime-based construction was so universal it was simply called mortar. There was no alternative. Then, in the mid-1800s, Portland cement was invented, a faster-setting, higher-strength alternative. By the mid-20th century, Portland cement had almost completely replaced lime in new construction. And that's when the problem started. Section 2. Why lime mortar outperforms modern materials. Lime mortar has several properties that make it superior to Portland cement for long-term durability, especially in traditional masonry and restoration. Property 1. Self-healing through recarbonation. When lime mortar develops hairline cracks, inevitable in any structure due to settling, thermal expansion, or minor movement, rainwater enters the cracks and dissolves a small amount of free lime. That lime is carried through the crack by capillary action, then recarbonates when it encounters CO2 in the air, effectively healing the crack by depositing new calcium carbonate. This process can continue for decades or centuries, as long as there is moisture, air, and remaining free lime in the mortar. Medieval cathedral mortar is still slowly carbonating and strengthening today, 800 years after it was mixed. Portland cement cannot do this. Once it cracks, it stays cracked. Water penetration leads to freeze-thaw damage, rebar corrosion, and progressive deterioration. Property 2. Breathability and moisture management. Lime mortar is porous and vapor permeable. It allows moisture to migrate through masonry walls and evaporate, preventing trapped water from causing freeze-thaw damage, rot, or salt efflorescence. This is critical in historic buildings built before modern damp proofing. Stone and brick walls were designed to breathe, to absorb moisture during rain and release it during dry periods. Lime mortar enables that cycle. Portland cement, by contrast, is dense and impermeable. When used to repoint old stone or brick walls, it traps moisture behind it. The stone or brick, softer and more porous than the cement, absorbs water that can't escape. In winter, that water freezes, expands, and blows the face off the stone. Conservators call this cement cancer. It's the leading cause of accelerated decay in historic buildings that were repointed with modern cement in the 20th century. Property 3. Flexibility and accommodation of movement. Lime mortar remains slightly flexible throughout its life. It can accommodate minor movements, settling, and thermal expansion in masonry without cracking or failing. This flexibility also allows it to bond effectively with softer, more porous historic stones and bricks. Portland cement is rigid and strong. When movement occurs, cement doesn't flex. It cracks. And because cement is often harder than the adjacent stone or brick, the crack propagates through the masonry units themselves, causing structural damage. Property 4. Compatibility with historic materials. Stone and brick have specific physical properties: porosity, thermal expansion coefficients, compressive strength. Lime mortar was developed alongside these materials over millennia, and its properties are naturally compatible. Portland cement is far stronger and denser than most historic masonry. This strength mismatch causes stress, concentrations, and differential movement. Instead of the mortar acting as a sacrificial fuse that fails first and can be easily repointed, the stronger cement forces stress into the stone or brick, causing irreversible damage. Property 5. Lower embodied energy and carbon footprint. Lime can be fired at lower temperatures than Portland cement and reabsorbs much of its production CO2 during carbonation. Portland cement production is one of the largest industrial sources of carbon emissions globally. For anyone concerned about sustainability and long-term environmental impact, lime's lower energy input and carbon-negative curing process make it dramatically superior. Section 3. The historical record. Buildings that refuse to die. The proof of lime's superiority isn't theoretical, it's standing all around us. The Pantheon, or Rome, 126 CE. The world's largest unreinforced concrete dome, built with Roman lime concrete, opus cementitium, mixed with volcanic ash. Nearly 2,000 years old and still structurally sound with no major repairs to the dome itself. Gothic cathedrals, 12th–16th centuries. Notre Dame, Canterbury, Chartres, Cologne. Built entirely with lime mortar bonding limestone or sandstone blocks. Despite wars, fires, and centuries of weather, the mortar joints remain strong. Medieval castles and fortifications, stone fortresses built with lime mortar across Europe, the Middle East, and Asia have survived 600 and 1,000 years of sieges, earthquakes, and neglect. Roman aqueducts and bridges. Lime concrete structures like the Pont du Gard in France, 1st century CE, still carry water or traffic after 2,000 years. Compare this to modern reinforced concrete, which has a design life of 50–100 years. After that, carbonation reaches the rebar, corrosion begins, the rebar expands, and the concrete spalls and fails. Highways, bridges, parking garages, and buildings built in the 1950s–1980s are now reaching end of life and require massive repair or replacement. The infrastructure crisis in developed nations is largely a crisis of concrete deterioration. Lime structures from the medieval period, meanwhile, are still going strong. Section 4. Why the switch to Portland cement? If lime was so superior, why did the construction industry abandon it? The answer is speed, strength, and industrialization. 1. Speed. Lime mortar cures slowly, weeks to months for initial set, and months to years for full carbonation and strength gain. You cannot build a skyscraper or pour a highway on that timeline. Portland cement sets in hours and reaches working strength in days. This allows rapid construction cycles, faster project turnover, and higher profit margins. 2. Compressive strength. Portland cement achieves very high compressive strength, often 3,000, 5,000 plus psi. This is essential for modern high-rise buildings, thin concrete slabs, and heavily loaded structures. Lime mortar, by comparison, reaches only 200, 800 psi, depending on mix and curing conditions. That's more than adequate for masonry walls, but it can't support the loads required by modern steel frame or reinforced concrete structures. 3. Industrialization and standardization. Portland cement could be mass-produced, bagged, shipped, and used by less skilled labor with consistent results. Lime mortar required more knowledge about mixing, curing, and application, skills that were being lost as traditional masonry crafts declined. Rebar and reinforced concrete. The rise of reinforced concrete in the early 20th century fundamentally changed construction. Steel rebar allowed thin, strong structures impossible with masonry alone. But rebar requires the alkaline environment of Portland cement to resist corrosion. Lime's lower pH doesn't protect rebar as effectively, so the entire construction industry pivoted to Portland cement as the default material for nearly everything: foundations, walls, slabs, roads, bridges. By the 1960s-70s, lime mortar had almost disappeared from new construction. It survived only in specialized restoration work on historic buildings. Section 5. The Reckoning. When modern materials fail. The consequences of abandoning lime became visible in the 1980s and 1990s as the first generation of post-WPU concrete infrastructure began to deteriorate. Concrete cancer in bridges and highways. Reinforced concrete bridges built in the 1950s-70s started showing severe spalling, exposed rebar, and structural cracking by the 1990s. Investigations revealed that carbonation and chloride penetration from de-icing salts had reached the rebar, causing corrosion, expansion, and concrete failure. Many of these bridges are now at or past their design life and require costly repair or replacement. In the U.S. alone, the American Society of Civil Engineers estimates a multi-trillion-dollar infrastructure repair backlog, much of it related to concrete deterioration. Accelerated decay in repointed historic buildings. Starting in the mid-20th century, well-meaning but misinformed contractors began repointing historic stone and brick buildings with hard Portland cement mortar instead of lime. Within 20 to 30 years, the results were catastrophic. Stone faces spalling off, brickwork crumbling, moisture damage, and freeze-thaw cycles destroying walls that had survived centuries with lime mortar. Conservation professionals now universally condemn cement repointing of historic buildings and advocate for lime-based repair. But the damage is done to thousands of structures. Sustainability crisis. Concrete production accounts for roughly 8% of global CO2 emissions. As awareness of climate impact grows, the construction industry faces mounting pressure to reduce its carbon footprint. Lime-based materials, with lower firing temperatures and carbon-negative carbonation, offer a clear path to lower impact. Construction, but adoption remains slow. Section 6. Why modern engineers fear lime. So if lime mortar is proven to be more durable, sustainable, and appropriate for many applications, why don't modern engineers embrace it? The answer is institutional, economic, and psychological. Reason 1. It doesn't fit modern project timelines. Modern construction operates on tight schedules dictated by financing, labor costs, and contract penalties. Lime's slow curing time is incompatible with these timelines. Contractors cannot afford to wait weeks for mortar to set when cement can be ready in days. Reason 2. It doesn't meet modern building codes. Building codes in most countries are written around Portland cement specifications, minimum compressive strength, set times, and performance standards. Lime mortar often doesn't meet these standards, not because it fails in practice, but because the codes were written for cement. Getting approval to use lime in new construction requires special engineering analysis, testing, and bureaucratic waivers that most developers won't bother with. Reason 3. Lack of skilled labor. Traditional lime mortar mixing, application, and curing require craft knowledge that has largely disappeared. Modern masons are trained to work with cement. Reintroducing lime would require retraining an entire workforce. Reason 4. Lower compressive strength is seen as weakness. Engineers are trained to maximize strength and load capacity. Lime's lower compressive strength looks like a liability on paper, even though its flexibility, breathability, and self-healing properties make it more durable in real-world conditions for many applications. Reason 5. Fear of liability. If an engineer specifies lime mortar and anything goes wrong, even if unrelated to the material, they risk being blamed for using outdated or inferior materials. Specifying industry-standard Portland cement provides legal cover. Reason 6. Economic incentives favor replacement over durability. Perversely, the construction industry benefits from shorter building lifespans. If structures last 50-70 years instead of 500-700s, there's more repeat business, more repairs, more replacements, more contracts. Building with lime mortar that lasts centuries doesn't generate the same revenue stream. Section 7. Where lime is making a comeback. Despite these barriers, lime is experiencing a quiet renaissance in certain sectors. Historic preservation and restoration. Conservation architects and masons working on historic buildings now universally prefer lime-based mortars and plasters. International guidelines, like those from UNESCO and ICOMOS, explicitly recommend lime for repointing and repair of pre-20th century structures. Specialized suppliers now offer hydraulic limes, pre-mixed lime mortars, and technical support for restoration projects. Natural and sustainable building movements. Builders focused on low-impact, breathable, and healthy construction, especially in Europe, are reviving lime plasters, lime renders, and lime hempcrete construction. These projects prioritize long-term durability, indoor air quality, and carbon footprint over speed and cost. Seismic retrofitting. Surprisingly, lime mortar's flexibility makes it superior to rigid cement in earthquake-prone regions. Flexible lime joints allow masonry walls to move and dissipate energy without shattering. Some engineers working on seismic retrofits of historic buildings now specify lime-based repair mortars specifically for this reason. High-end residential and custom projects. Wealthy clients interested in heirloom construction, buildings meant to last generations, are increasingly specifying lime-based materials, traditional stone masonry, and craft-intensive techniques. These projects accept longer timelines and higher upfront costs in exchange for structures that will outlast conventional buildings by centuries. Section 8. What you can learn and apply. Most viewers won't be building stone castles, but you can borrow principles from lime-based construction for modern projects. For historic home repair, if you own a pre-1900 building, insist on lime-based mortars and plasters for any restoration work. Do not let contractors use Portland cement on historic masonry. It will cause long-term damage. For new masonry projects, consider hydraulic lime mortars for garden walls, outdoor ovens, stone patios, and other non-structural or lightly loaded applications. These will breathe, self-heal, and outlast cement alternatives. For plasters and finishes, lime plaster is making a comeback in high-end interiors. It's breathable, naturally antimicrobial, beautiful, and improves indoor air quality compared to synthetic plasters and paints. Support skilled tradespeople. Seek out masons, plasterers, and builders trained in traditional lime techniques. By hiring them, you help preserve and pass on craft knowledge. Advocate for code reform. Push local building departments to recognize lime-based materials in codes and allow their use without excessive bureaucratic barriers. Section 9. The deeper lesson. Time horizons and permanence. The story of lime mortar versus Portland cement is really a story about how we think about time. Medieval builders designed for permanence. They worked on cathedrals that would take a century to complete and expected them to stand for a millennium. Lime mortar. Slow curing, self-healing, strengthening with age, matched that mindset. Modern construction optimizes for speed, cost, and near-term profit. Portland cement, fast setting, high strength, disposable within a human lifetime, matches that mindset. Engineers don't fear lime because it doesn't work. They fear it because adopting it would mean admitting that the entire modern construction paradigm is built on planned obsolescence. That mortar doesn't demand replacement every 50 years. It doesn't spall in winter or corrode its reinforcement. It breathes, flexes, and heals itself. It gets stronger with every passing decade. Modern engineers know this. They've tested it. They've seen the historical record. They know lime mortar is, by every long-term metric, superior to the materials we use today. But they're afraid to say it out loud. Because if lime is better, then everything built since 1950 is a planned failure. The material that modern engineers fear is the same material that built empires, survived wars, and quietly outlasted every modern improvement we've invented. Maybe it's time to stop being afraid